Okay, so yesterday we played around with getting the different forms of the equations of a plane in R3. And we did a couple of different examples. And I want to continue on with that and explore a little bit more what we can do with planes. Um, so imagine, well, there are the four cases. So I'm going to list out those four cases that you could start with potentially that I could give you. So there were four cases. What we're going to do is we're going to just kind of talk about how you would proceed in each of those cases. We're not necessarily going to do one of each of them right now. But we're going to talk about the strategies, and I would really, really like you to, pause the video after each, scenario and think about how you would move forward. I'm going to write it down, but it makes a big difference for you to make those connections on your own. So four cases. So first case that we could deal with is three non-collinear points. So if I gave you three non-collinear points, how would you go about getting any of the forms, or alternatively each of the forms of the equation of the plane defined by those? So go ahead, pause it, think about it, and then come on back. Well, we've already done this one, right? So what we're going to do is we're going to, for that, we're going to find two direction vectors between the points, right? So if the points are A, B, and C, we could do any of them, right? So we could do AB, we could do AC, we could do, BC, we could do BA. It doesn't really matter, right? As long as you find two of them that are not collinear. Now, you couldn't find AB and BA because they would just be the same vector. They would be opposite vectors. They would be, totally collinear. So you're going to find two direction vectors between the points. And then, one of the points. So you know a point already. And so then we've got, that it's going to be X, Y, Z equals, and then, just any point. So a P naught that's any of the 3 points. Plus S times direction vector 1 plus T times direction vector 2, that, this could be D1 and this one here could be D2, for instance. And there is the vector equation. Certainly, once you have the vector equation, the parametric equation is trivial. I'm not even going to discuss that. But then to get the Cartesian equation, the Cartesian equation process is going to be the same in each time. We're going to find the Cartesian by saying the normal is equal to direction vector 1 crossed with direction vector 2. And then, we wrote the steps down. So then we're going to, then you have AX plus BY plus CZ plus D equals 0. You're going to substitute in your normal vector. So there's your normal vector, there's your normal vector, there's your normal vector. So those are, your normal vector. And then you're going to take any point, right? So any one of the points and put it in there. So those are going to be any point, and then solve for D. Right, and there it is. Okay, so that's the case when we have three non-collinear points. How about the case 2? And that is the intersecting lines. Well, the vector equation is pretty much a gimme, right? So the intersecting lines vector equation is trivial. So vector equation, you're going to just, take, P naught is a point. And it's normally going to be, it doesn't always have to be, but it's, is a point. It can be any of the points. If you know that these two lines intersect, then, Bob's your uncle, you're good to go. You can just choose either of the points, either of the P naughts from the line. Often they'll be the same, but there's no necessity for them to be the same. So P naught is just any of the 2 points that you have access to. And then the direction vectors from the line. Right, so that one, that's why we started with that one, right? That's the easy one. It's a gimme, and then, Cartesian is the same deal, right? So there's your Cartesian, same thing. You're good to go. 3, parallel lines. Well, for parallel lines, we know, either of the points. So either anchor point, for our current anchor point, so either of the anchor points from L1 or L2, and we know a direction vector. It's going to be the same direction vector for the two because they're parallel. So a direction vector from the lines. And then we need to get a second direction vector by using the two anchor points and finding the vector between them. Okay, so pretty trivial. And then, of course, the Cartesian equation found the exact same way again. And then the fourth case was a line and a point. And we didn't talk about that one, but hopefully, if we think about what that kind of looks like. So here's our line, and here's a point. Our line, there must be some P naught on there, right? So there's a P naught, and it must also have a direction vector, right? And so there's got to be a direction vector on there, right? So there is a direction vector, right? So what we then need to get is all we need to do is get a second direction vector. Well, what we're going to do to get that second direction vector is we're going to take and find, so this is just going to be any old point on the line. We're going to take and we're going to find the vector that goes from the anchor point on this line to this one over here. And there is going to be our second direction vector. And I think I'm not even going to write it out because, there it is right there. Right. So, I want to practice that, so I'm going to give you a scenario right now of these ones. And there we go. So what I'd like you to do is, given the line, and I'm going to give it to you in a different form. So given the line, how about x minus 7 over 3 equals y plus 2 over 4 equals z over 5. So there's the line. And the point 1, negative 4, 6. I'd like you to find all forms of the plane defined by the line and point. Okay, so I've given you, this is the equation of a line right here, right? This guy here is the equation of a line, and there is another point. So effectively, I've given you that case that I just drew up there. I'll draw another one, so I've given you a line and I've given you a point. And I want you to find, the vector equation. I want you to find the parametric equation, and I want you to find the Cartesian equation. So go ahead, pause this, and give it a whirl. Okay, so first thing that would I? I probably, no, I probably would. First thing I would probably do is this is the symmetric form of the line. And while you can kind of look at that and spot what it is, I think it's probably in your interest to get it into vector form. So the first thing I would do is I would convert this into the vector form of that line. So I'm going to convert symmetric to vector form. Okay, this is my solution. So that's the first thing I'm going to do. So I'm going to say, all right, that would be x equals 7 plus 3t, and that would be y equals negative 2 plus 4t, and z equals 0 plus 5t. Right, so I would first go to, even though it says from symmetric to vector, I would have that intermediate step, which takes me to parametric, and then I would go to vector just because I find it easier. And so then I would say, all right, well, the vector form is x, y, z is equal to 7, negative 2, 0, plus t times 3, 4, 5. So there is the same equation just written in vector form. Now, I realistically, I probably would have jumped from here down to here because I can see, oh, I know the signs are going to change. So it's going to be 7, -2, 0. So 7, -2, 0. And then the denominators form the direction vector 3, 4, 5. But, it's probably good exercise to go through the intermediate step of getting the parametric equations as well. Okay, so there we have the vector equation of the line. But I want the vector equation of the plane. Well, I know the vector equation of a plane looks like x, y, z plus equals some p naught plus s times direction vector 1 plus t times direction vector 2, where s and t are both members of the reals. Okay, easy peasy. So let's kind of go through and see what we've got. So we've got x, y, and z. That's just the any or every point on the line. And then p naught is any point on the plane. Well, we've got a couple of choices. By definition, we said this point is on the plane, so I could absolutely use 1, -4, 6. But this whole line is on the plane, and this point is on the line, so that means that this point is on the plane too. So there is a second easy candidate that we could use to put in as our P naught. Now, those are not the only choices. Those are the ones that, I like when students use because it's pretty obvious to me. In theory, we could put any parameter of t in here that we wanted. We can make t, an obvious one. Be like if t was 10, so that would mean that the point 37, 38, and 50 is also a point that's on this line, which because the line is on the plane, it means the point is on the plane. So you could just as easily use that point there. So there's an infinite number of different anchor points that you could use, but I'm going to go with an easy one, which I'm going to go with 7, -2, 0. So 7, -2, and 0 plus s. And I need a direction vector. Well, I know one direction vector is right there. It's 3, 4, 5, right? 3, 4, 5 is one of my direction vectors. Easy peasy. Plus t times, and I need another direction vector. Well, I don't explicitly have one. However, I know that this point is on the plane, and I know that this point is on the plane. So that means that the vector that goes from this point to this point, or from this point to this point, must also be on the plane. And so I know that I'm going to want it to be positive. So I'm going to go from 1, 4, 6, 1, -4, 6 to 7, -2, 0. So to go from 1 to 7 is up 6. To go from -4 to -2 is up 2. And to go from 6 to 0 is down 6. Now, unfortunately, I thought I was being smart, and it was better than having a negative, but this isn't in lowest terms. So I would want to do x, y, and z is equal to 7, -2, 0 plus s times 3, 4, 5. We're good there. Plus t times, well, this is going to be 3, 1, -3. So there it is. There is the vector form of that plane. Okay, so there's the vector form. We get the parametric form, which, by now I hope you feel it's pretty easy. So it's going to be x is equal to 7 plus 3s plus 3t. And then we're going to have y equals -2 plus 4s plus 1t. And then we're going to have z is equal to 0 plus 5s minus 3t. So there is the parametric form. Easy peasy. And then into Cartesian form. So Cartesian form can, I know I'm going to need the normal vector. So I know that the normal vector comes from the cross products. So the normal vector I'm going to find by doing the cross product of these two vectors. So 3, 4, 5, 3, 4, 5, 3, 1, -3, 3, 1, -3, go away, go away. So we're going to have -12 minus 5, which is -17. And then we're going to have, I guess, 15 plus 9. So 15 plus 9 is 24. And then we're going to have 3 minus 12. 3 minus 12 is -9. So I have found, if I've done it correctly, that the normal vector is going to be equal to, not very nice numbers, -17 24, and negative 9. And while that is a normal vector, the one that we want has to be both in lowest terms and have a positive leading coefficient. So I'm going to make that 17, negative 24, and 9. Now, I would, if I was responsible, and I guess I'm going to be, I would make sure that if I dot product this with, well, frankly, both of them, but with either of them, it needs to come out with a 0. So that would be, oh goodness, so 30 and 21. So 51 minus 24 minus 27. So minus 24 minus 27 is negative 51. So that's good. Yeah. So, there's my normal vector. I'm good about that. So then we know that the equation of this plane is going to be, it looks like 17x minus 24y plus 9z plus d equals 0. And then we're going to take a point. Now, certainly any of the points that are on the plane will work. I'm going to use that one because it's got a 0 in it, which will make my math a little bit easier. So 17 times 7 minus 24 times negative 2 plus 9 times 0 plus d equals 0. And so 70 and 49 is 119 plus 48 plus 0 plus d plus 0 plus d equals 0. So that's 150, 167. So I think d equals negative 167. Now, none of that's all in my head, so there's a good chance that I made a mistake, but the process remains correct. So 17x minus 24y plus 9z minus 167 equals 0, I believe is the equation of that plane, which admittedly is not terribly nice, but it is, the equation. Now, if I wanted to test it, and I'm not going to do it right this moment, but if I wanted to test it, a good way to test it would be to take this other point, this 1, negative 4, 6, and put in 1, negative 4, 6 onto the left side and make sure that it yields a 0. Well, maybe I will do that. It'll be exciting because I don't know if I did it right or not. So left side is going to be equal to 17, and then it was 1 minus 24. What was it? Negative 4, I think. Negative 4. Well, this I'm tense because I might have made a mistake along here. And this will be embarrassing, but you can laugh at me, which is always good. And then 6, I think, was it plus 9? Yeah, 6. And then minus 167. Minus 167. And then the right side is just 0. So if I've done this correctly, when I type this into my calculator, I'm actually have to grab a calculator because I'm not going to do that in my head. It should come out to be 0. Did I get it? No, I did. There we go. All right, back we go. So exciting times. Let's see. So 17 times 1, so it's just 17, minus 24 times negative 4, plus 9 times 6, minus 167. Oh my goodness. Tense, tense, tense. Woohoo! 0. So I did it, right? So that just validated two things. So that's 0. So we got the left side equals right side. So I feel pretty darn good. So I'm going to go with a huzzah with the optional H at the end because I feel good about that. And so then I validated it, right? So then we're good to go. So these are the 4 different ways that we can get into getting an equation of a plane in R3. Now we are going to progress on. And we're going to talk about one more concept on this video. Now I'm going to keep this one shorter simply because, well, my girls are going crazy in another room. And also, I think that last one was pretty big. And if you did the homework questions, it probably took you much more than an hour. The other thing that we can do is we can calculate the angle between 2 planes. So I'm going to go and I'm going to try and draw this, and you can definitely laugh because it will be a garbage drawing. However, so here's the scenario I'm talking about. So we've got a plane, right? So here is a plane. And then we've got some other plane that goes through this plane. So I might as well make this straight too, I suppose. That makes sense. Like this. And then keeps going. And then shouldn't be able to see in there. I'll fix it in a bit. Make it like this, I guess. I don't know. I am not an artist. So it goes like this. Right. And so what we've got is there's two planes. Now, obviously, they're not defined quite like this simply because um, obviously they are going to be, going forever in every direction. Right. So something like that. That's terrible. But nevertheless, imagine that we, lined ourselves up from a side view. What we would have is it would look something like this, right? So we've got our two planes. Um, so I want to know what the angle between these two planes is. So there's be an angle that's formed right there, right? Where this is a line on this plane. So there's an angle that's here. So maybe I'll do some different colors. So there's an angle right here between these two planes. So, kind of this angle right here. And then we've also got, I don't even know what the color that is, this one. Then we've also got the angle that it makes here between the two planes. Now, obviously, whatever color this is and whatever color this is, if I added those two angles up, hopefully it doesn't take grade 12 calculus to realize that those two angles should add up to 180. And this one corresponds to this angle over here. So the question becomes is how do we find out what the angle between the planes are going to be? Now, this is where it gets interesting. I can't just use the direction vectors on the planes because I wish I knew what color that was. Let's pretend it's black. I don't know if it is or not. Imagine that if we thought about this plane right here, right? So I'll call this one plane one. Plane one might have been defined with, there's my P naught on plane one, and I had this direction vector. That's not a direction vector. I had this direction vector that I used, and then I also used this direction vector, right? Because all I need is a point on the plane and a couple of direction vectors for the vector equation. So, maybe that's the definition of this plane. And then this one up here, I'll call this one, let's get a different color, this color. This is going to be P2. Maybe P2 used this and then this direction vector and this direction vector, right? That would be enough. So if I just use direction vectors, if I use this vector and I found the angle in between them, that'd give me one answer. Or if I used this one and this one, that'd give me an answer, right? You can imagine that there's a load of different answers that we could get depending on what direction vectors we use. So hopefully you could kind of think about what we would maybe do. And what we would do to solve this one is to consider the angles made by the normals. Now, it's not going to be easy for me to do this, but I'm going to try and draw these in. So imagine we've got a normal vector to plane 1, right? So this is at right angles to plane 1. So I'm going to call this one normal vector 1. And then, I don't remember what color that was, something like this. We have a normal vector to the other one. Oh, I didn't get the color. So a normal vector to plane 2, right? So there's theoretically the normal vector to plane 2. So I'm going to call that one N2. Well, the angles between the normal vectors, right? Oh, I don't know what color that is now. It's like greenish or something. I don't know, like that match it. Not even close. But, this angle would match this angle. And then I can't really show it right now, but, if this vector kept on going, that angle would match that angle, right? And so the normal vectors, they're both 90 degrees to the plane, but because they're both shifted 90 degrees, the angle between the normal vectors can actually tell us what the angle between the planes is going to be, okay? And so we're going to revert back to finding the angles between two vectors. And remember, depending on which one we wanted to use, we know, I always, I still would probably derive it on the fly. I know that vector, if I'm going to go direction vector 1 dotted with direction vector 2, it's equal to the magnitude of d1 times the magnitude of d2 times the cosine of theta. So I can then rearrange that and I can say, oh, that means the cosine of theta is equal to d1 dotted with d2 divided by the magnitude of d1 times the magnitude of d2. But in this case, obviously, we're going to use the normals. So we would do the exact same thing, but we would say the cosine of theta is equal to n1 dotted with n2 divided by the magnitude of n1 times the magnitude of n2. And that's going to tell us. Now, I could ask the question, I could say, what is the acute angle between the two planes? Or I could say, what is the obtuse angle between the two planes? And we would solve it the same way. And when we do, cos inverse of this to find out what theta is either going to be obtuse or acute. And you can find the other one by subtracting it from 180. So it's a pretty trivial task to do. So I am going to lob some homework questions out of the textbook at you, and say, bid you adieu for the week. So this is going to be page 469, numbers 6 through 13. And again, I want to reiterate that anytime you have any questions with this stuff or any troubles, by all means, please, please, please shoot me an email or put it up on Google Classroom, and I will go and make sure to address it. I hope you all have a lovely week.